Hello, everybody. Okay, got the camera sitting at a higher angle. Hopefully that'll make the board a little easier to read. I can move it over just a little, get a little more straight on. That looks pretty straight on. It looks a little more square with the edge of the thing. Hopefully this will make the board easier to read. So, moving on with our material. That was something pointed out in one of our interactive Zoom sessions for those who weren't there Wednesday night, the first week. So we'll try this. Please let me know any feedback about reading things off the board and whatnot. That's for you all. I know what's on the board already, so if there's something I can do to make it get across in the video a little bit better, just let me know. So the new material here. So let's think about a picture stepping away from programming and just completely generalizing some ideas. So let's take and consider a table. It's a nice basic thing we've all seen before, right? Table's got a few parts. We have the tabletop, not a real fancy table here. And leg coming down, and then we'll have legs coming down in each corner, right? Something like that, just a basic table. Not this is the fanciest thing. But with what we've been doing so far, it's kind of like we did this for our table. We'd design a top, and then the top of a table has to sit on something, right? So then we'd design a leg. One leg's not going to hold up a table. Then we design another leg. Design another leg. Design another leg. And kind of go through all of that, and then we put the pieces together. Kind of what we've been doing so far, right? Building every single little piece, and if we need to do something a bunch of times, we just do it all those times. We kind of looked at loops last time, but even inside the loop, we just keep doing it over and over and over again. This is kind of redundant, right? In this picture, it's not the best picture, but those legs are supposed to all look the same there. So we got a little bit of a redundancy going on there. That we have 3 different legs going on. A better approach is to cut out the redundancy, right? Design the top of our table, something like that. Design leg, well, all our legs are going to be the same. And then finally, put that together, right? Build top, ask for leg, 3 times. Oh, 4 times. 3 more times. I should probably put 4 here, though. Then we're not repeatedly designing the same thing over and over and over again. We design it once and just ask for it several times. That'd clear out the redundancy. And allow for expandability, right? We could expand it at that point. We could ask for, I don't know, 3 tops and 9 legs. Make a really big table without having to design anything new. So kind of a better method for putting this stuff together. That's the first one, first little consideration issue here that we're going to start off with. Put an edit point in the video and erase the board, and then do the next consideration. So hopefully that's more readable, so I'll stand over here out of the way so that you can hopefully copy that down. And now I'll reach over here and put it in an edit point. So the next thing that we might want to consider now that we've seen some of the basic syntax, well, involving that basic syntax. A couple videos back, I mentioned that thing that we know we'll need that will work to solve any problem, the 4 constructs. The first one being sequence. The second, select. Third, reiterate. And fourth, invoke. So I discussed a couple videos back how these concepts are enough to solve any problem. An order to go in, a way to make choices and decisions, way to repeat things, and a way to jump out of our order and back into it the same spot we left it. Well, we've seen these, right? Sequence in programming is pretty much trivial. We start at the top and work down. Selection and reiterate. We saw those last week. Selection structures and reiteration structures are if, elif, else blocks in Python, or while and for loops. We haven't really looked at for loops much. We looked at a while loop in the example. The book talked about for loops to put them together. The second lecture of this in the third module here is going to be over list and getting into things like lists, and for loops are a lot more useful and make more sense there. So I just kind of pushed that back I also figured there'd be more time to talk about it in that video than the previous one. But we've seen 3 of those. We still need a way to call up our 4th construct, invocation, a way to jump out of our sequence, do some other stuff, and come right back to the spot where we left out of the sequence. And yeah, so what we're getting into is functions or methods. Those words are interchangeable. Throughout this lecture, I will probably be jumping back and forth between them interchangeably. Unless one of them is a keyword in the language, and even in that case, when we talk about them, they're still interchangeable. It just means the same thing. So functions or methods, whichever way. Really, one of the core concepts of English. Whichever way is easier to say is the way that it's going to work into that sentence. They mean the same thing. A short definition here for this. Let's just think of this as reusable blocks of reuse. I'll start with independent. Independent reusable blocks of instructions. So reusable independent blocks of instructions. That's what we're going to call functions and methods. Typically, small things that wouldn't stand on their own. Pieces of something. We're going to take a big program and break it up in pieces and then basically label each piece separately so that we can ask for it as needed. But that's not a restriction. We could make a method that is entire program in one method, but typically small things that aren't going to stand on their own, that go with other small things. And again, the terms are interchangeable, whichever one we want to use for a line of code is fine for describing it. And even if we're not going to be using our functions reusably, I'll add another point here. Put a solid line. I've noticed the dashed lines don't separate very well when they go that way, when they go horizontal. Even if we're not going to be using them for reusability, they really help to organize. Even if we're only going to use that function one time, it's only going to show up one time in one program, it still helps to organize our code. Makes it easier to debug. Makes it easier to debug. Makes it easier to debug. Or find problems. Or, and this is something more in the long term, when, the classes have lots of homework examples, we finish homework, turn in, move on to the next one. But in the long run, you're going to be working on projects and you're going to keep them going, right? So, like, oops, I spelled that wrong. Update or upgrade. It's going to make our software a whole lot easier to update and upgrade too, because then the functions that don't need change can stay like they are, and all the updates go into replacing the functions, just the parts that need changed. The little independent blocks, we can deal with each section independently of the others. So when we go to upgrade it or update it, we don't have to redo the entire thing. We can just upgrade or update that one method, or the methods one at a time. Probably an update's probably going to be more than one. Excuse me. That's some of the core ideas. So we'll finish out the last piece of the 4 constructs that we'll need, so that we'll have the tools to solve any problem. It's going to show up in every language. It's a common thing in every programming language. And these words are interchangeable. And organization is a big deal. Not just reusability. It organizes it, makes the code easier to work with. So we'll now erase the board, and we'll get started into some talking about functions and methods directly. So as we get started here into some generalizations, we'll be to Python specific stuff in a moment. Just some generalizations on functions and methods in different languages. One of the first points we want to consider is, again, back to the difference between compiled and interpreted languages. This is something we talked about at the beginning, but it really kind of stands out here. It makes a big difference with methods. So compiled language, machine has entire file. So if the method is there, the machine knows about it. If method is in file, machine knows about it. The big thing this is leading to is order doesn't matter. The order does not matter. Just to be, I'll spell does not instead of doesn't, just to be very clear on that. The order in a compiled language, the order we put our methods in does not matter. The machine has the whole file. If the method's in that file, it'll find them. It'll find it. An interpreted language, on the other hand, remember, runs line by line. It runs the first line, does that. Then it runs the second line, does that. Line by line. So if method is written I'll capitalize this. After, if the method is written after our call to it, then the machine doesn't know about it. Because the machine starts at the top first line, does all that, then goes to the second line, does all that, goes to the third line, does all that. So if it's written after our call, the machine will not know about it because it hasn't gotten to it yet. After our call to it, the machine won't know about it. So in an interpreted language, the method has to be written before any calls to it. Otherwise, the machine won't know about it. At the point we're at now. The point we're at now, it has to be written before, where we start at the top and put everything in one file. This restriction won't apply in objects. So this won't apply to objects, and there is a quick workaround we'll see at the end right before we jump into examples. And we'll see it in one of the examples. But put methods in a different .py file. The modules, we saw those we saw importing modules already. We can create another module that has all the methods we'll need. And this works because import line is first. I'll just write that because I'm running out of space. But our import line is definitely going to happen before any calls we make to functions. So if we put all our methods into another module, a separate .py file, and just import that, then we don't have to worry about it being written after because the import happens first. As a quick workaround and object-oriented as well, it's going to have the entire object there before it starts working with it. So that's just some things to keep in mind, not just in this class, but as you move forward, work with and learn to work with more languages. Keep in mind whether you're in a compiled or interpreted language when putting your functions together. Interpreted languages do have this restriction on them. So getting into methods here, still in the generalizations. So regardless of language, I'll just write in any language. In any language, no matter which one we're working in, methods have two parts. So the first part is the method header. So this is going to have our language-specific keywords. The syntax we need to set up a method in that particular language to tell the machine we have a method. We'll have the reference name, the name that we're going to ask for when we want that function to run. And it'll have any parameters needed. Anything we need that needs to be passed into that method for a particular run case of it. We will define that in the method header. Our second section will be the method body. And this basically has our instructions. The instructions we want to run when we ask for that method. And obviously any syntax for defining a block of code or blocks of code and lines, which is nice in Python because we define lines by a line break and we define blocks by indentation. It makes it a good language to learn with. Those things are easy to work with. Defining a line by a line break makes sense to a lot of people, to most people. So that's the two sections we have no matter what language we're working in. We have a method header, which will have our keywords and some syntax, the stuff telling the machine that we have a function to call. A name that we're going to ask for it by, and then the list of the parameters that the method will need. If it's going to need a number to work with inside, we want to have a spot to pass that in. So places to accept parameters, and then the method body is just our instructions. And when we want to use a method, our general vocabulary term is we call it. We call that method. Every once in a while I get a sentence up there on the board. It's like, wow, I really should have thought through that sentence before writing it, but it's not the worst grammar I've ever jotted down. But to use a method, we call that method. That's our general vocabulary term for that. And looks like I have a little bit of space here, so our unified modeling language symbol for a method is going to be like a processing rectangle, only with double walls on the side. That's what a method call looks like. And I'll just do one with no parameters passed in. Parentheses have kind of become our generalized symbol for do something, right? Without parentheses, that usually means we have a variable. With parentheses, that means we have a function we're going to do something, is how I like to think of that. And any parameters we need go inside the parentheses. We'll see that when we get to examples. That's fairly standard across languages. There are still some old ones that have persisted. Hexadecimal colors. A lot of you may have seen that before, right? F2, 3, 4, 7B. I think it's going to be a purplish color. But this is an old syntax, and that's called a function, and then we pass in those arguments. So some old function calls still persist. But most languages have kind of generalized to this form. We give it a reference name, and then parentheses indicate it's a method, and we pass parameters inside the parentheses. That's our UML diagram to work into pictures. I think most everybody probably used Raptor in the SDEV 120 class, where we're putting the flowchart interpreter. Most of the symbols in there kind of match the standard. I believe Raptor used a big box look like that for the call symbol. Most of them were really close to the UML standards, but this is going to be our UML standard when we work that into diagrams for the standard international language of communication for many, many years now. So programmers all over the world, no matter what language they're learning it in, right now, introduction to software development students sitting in India, well, they're going to speak English, sitting in China, some maybe in Cairo, maybe up in Germany. We're all learning it in different languages, but we're learning the same UML schematics, the same diagram-based language to communicate with each other. That way, no matter what language we speak, we'll be able to communicate with each other. So one more generalization, looks like it'll fit here on the board too, and that's the type of methods. Again, we have two basic types. Our first one is a void. Does not return anything. Actually, I'm just going to write a void method, just does stuff, and that's it. It does stuff. Print things to the screen, write a file, read a file. Oh, read a file would return stuff. Write a file doesn't necessarily have to return anything. Nothing's coming back after we do it. When we print stuff to the screen, we don't need a result of that. We don't need a result to confirm that it printed to the screen. So a void function just does stuff. And our second main type is going to be a return function. That's why I hastily changed that original definition I started giving there, because I didn't want to use that word in that other definition. But a return does kind of that. It sends a value back. Sends a value back. Or maybe they go with this. A void function does stuff, and a return function calculates stuff. So obviously, as a result of that, something is coming back from the function. We need a place to put it. Need a place to put it. But a void function does stuff, a return function calculates stuff, and then sends that stuff back to us. So that's our two basic types, and all of this stuff is regardless of what language we're in. No matter what language we're typing in, all of this stuff is going to hold. One more section of generalizations, and then we'll get into Python-specific stuff and some examples. I'm going to erase the board. I'm going to step out of the way so that in case you need to copy any of that down, put that there for a second. Hopefully that's more readable with the laptop in a better position. I guess you can pause it if you need them. Go ahead and pause the video and get ready for the next section. Okay, so the final thing on this list of generalizations about functions and methods here is, well, talk about how when we set up our method in the method header, we're going to specify any parameters that the function needs, the values it needs to carry out whatever its instructions are. A lot of times those are going to come from somewhere else. So the method accepts parameters, and we pass in arguments to fill those parameters when we call the method. And there's basically three ways that we can pass arguments to a function. Pass by value. We can pass by reference. And the third way, I guess really if I would have wrote that sentence out here on the board, say there are three ways we can pass arguments to a function, I would probably grab a red piece of chalk, quickly cross out the three and write 2. Because the third way is not used so much anymore. Excuse me. The third way, it's still in use, it still exists, but it's not used as much as pass by value and pass by reference. And this is the only one we have in Python. So when we get to examples, that's the only one we need to worry about right now. Depending on what class you take next, this is the only one you have in Java. And here in a moment, I'll talk about the reason why it's only those two and why this one isn't used in those languages. Pass by address. So pass by value. That means we're passing a value in, but maybe not the same value that we started with. Well, it'll be the same value. That value, it won't be stored in the same memory location as the one that's passing it. So I'll draw some stack heap diagrams to represent all of these. The stack representing our instructions and the heap representing random access memory. So for pass by value, over here there's going to be some main method, and we'll have a variable, and since I'm writing on the chalkboard and not typing, I'm just going to use math class variables and we call it x. This variable x is pointing at some block of code, some block of bits, storing the data that x is that we ask for by saying x. If we want to pass that into another method, which will go up here on our stack, I'll just call this M1, and it's going to accept a parameter we'll call y. So then when we're working over here in our method 1, we have this variable y to work with. Well, to pass by value, that means we want what x is holding. And when we pass by value, we don't want to mess up what x is. So we're going to pass that in notationally. We're going to say pass x in. But essentially what that does is it's going to come up here and make a copy. And then y will reference that value. So we'll pass in, say we pass in x, but it's not the same block of bits that x is referring to. We copy that, passing by value makes a copy of that, and then that copy is what gets passed in for y. Maybe I should draw the line this way. So when we do this, like it comes over here to a copy and then passes it. Maybe that's a better way to draw that picture. So we're working with a copy. The key thing to note is changes in method do not affect original. So that's the important part. When we pass by value, whatever we do in the method does not change what happened, does not change the original thing that was passed in. Passing by reference, on the other hand, and I'll set up a stack heap diagram to represent this stuff. And I'll use kind of the same starting point. We have this main method, and inside that we have this variable x. Which, remember, a variable is just a named location for a spot in memory, so x refers to these bits over in memory storing that data. So when we pass by reference, well, I'll draw the next part of the picture there. When we call this method M1, it takes in the parameter y, it means we'll have a variable called y to work with here. Kind of what we're passing is this thing. that arrow pointing from the original variable to the block of bits. That's what we pass in for y. So then at this point, oops, y refers to that same block of bits, which is a very important distinction because obviously if it changes here, it's referring to the same block of bits as the same chunk of memory as the original. So in that case, any changes here are going to show up when we go back, when this pops off our stack and we're back to our main method. So changes in method will change the original. Any changes we make when we pass by reference, any changes we make in our method to that variable will be reflected when we go back to the method that called it. So pass by address, we don't do much anymore, but I'll go ahead and we're generalizing things, so I'll go ahead and put the picture up here. Well, some people still use it a lot. I mean, everybody's got their personal style. You don't hear about this as much. Python and Java have been the most popular languages for a long time, and Python, what we're doing in this class, only passes by value. Java only passes by reference, which is an important note. Sometimes that's going to be the deciding factor for which language to use. As you start designing it out, is your design, does it make more sense to pass by value or to pass by reference? Because if your design it makes more sense to pass by reference and then do a whole bunch of stuff in methods and just keep those same, basically working with the same spots in memory over and over again, no matter what method's doing it, then you're probably going to use Java. If it makes more sense to pass by value so that you can get back to the original if you need to, then it makes more sense to use Python. So that's kind of maybe a deciding factor about when to use which language. So again, we have our main method here. Only this time, I'm not going to draw a variable referring to a block of memory. I'm just going to put a block of memory over here. It's somewhere over there. And when we call our method that's expecting a parameter to be passed in, we're just going to tell it which block of memory to use. Directly, explicitly state, use that block of memory. Gives us a lot more power over what the machine's doing and controlling it. The reason it's not used so much anymore, and part of the reason that Python and Java are so popular, is Python and Java, the prime examples of these two, both have really, really excellent garbage collection. We don't have to go through and clean this up. So if we're doing this sort of thing, we have direct control over RAM. So anytime when we're finished with it, we have to write the code to clean that RAM up. That way it doesn't just sit there and waste space. The people who develop Python and Java both using those are the prime examples of Python's pass by value, only pass by value, and Java is only pass by reference. Both of them have really, really excellent garbage collection. It does all that cleanup in the background for us. That's why we don't have to worry about it, right? When we do our simple print hello world example, we don't have to follow that up with the last line in the code that says, now clear out the variable or clear out the spots in memory where you held those characters to spell hello world. We don't have to empty that manually afterwards. We don't have, all that happens in the background. That's just garbage collection. It has really excellent garbage collection. And so pretty much constantly throughout, garbage collection let's just say Python. Garbage collection in Python is constantly trying to clean up memory. Every time it gets a split second, it's going to look and see if there's any references or unused bits or variables, anything that it can take out of memory to clean that up. And well, especially in Python, Python's an interpreted language. So that garbage collection cannot predict what's coming up on future lines because those lines haven't been translated to anything the machine can make sense of yet. So that's why we only pass by value. So that way we don't inadvertently tell garbage collection we're done with the reference, and it deletes it when we still need it after we get back, when we get back to the calling method from the side. So that's why in Python we only work when we pass by value. But that garbage collection, that's a big deal. That is a real pain to work with too. It's so easy to forget stuff or make little mistakes and clean out the wrong thing when you're doing it manually. So having it run in the background is really, really nice. So Java and Python, pass by reference, pass by value. Definitely can't do this in either one because we definitely don't want garbage collection going through cleaning up bits that it thinks isn't going to be needed. Because there's nothing in the main method pointing to those bits, as you can see from the picture here. So that's definitely something garbage collection would latch onto. So that's kind of why we're limited in one or the other. I might as well mention it when we get to the end of the semester doing stuff in VB. In Visual Basic, when you're writing your functions, you actually put in the words by val or by ref. So you have both there. But it's mostly those two. This class, we're practicing all these concepts in Python, so we'll be doing it by value. And again, that's often going to be a spot where you decide which language to use, as far as whether it makes more sense to pass by value for your functions or pass by reference for your functions. So just a couple pictures there to keep in mind, help visualize how we move data from the caller to the method being called. So the quick recap on the generalizations here. Quick generalized recap. So let's say use functions. We'll use functions first off for that basic one of our four constructs. For our invocation structure. I'm putting an asterisk, not a number here. There's not necessarily a significance to this. This is just when we use these. For reusability of code, that way we don't have to type essentially the same thing over and over and over again. And organization of code. Make it a whole lot easier to debug something that's organized nicely into functions, because then when there's a problem, you can go right to that function. Or bypass a function and see if everything works without the spot where the problem showed up. And then later in the long term, for persistent projects, when you update it and upgrade it, you can do so function by function, method by method, rather than the whole thing at once. So that's when we want to use them. So the Python stuff. Doing this in Python, I'll go ahead and read off the notes here. First off, there is kind of an order to this one. Our method header will have the keyword def, DEF, or short for define. Method header has keyword def, or define. Two, I'm going to adjust this list here slightly. Everything I have on this list here goes in the method header. So the method header has, first off, the keyword def, which means define. Sorry, I think I completely changed up my syntax there, but when I look back at my notes, it made more sense to switch the list up this way because all of these things are in the method header. So first off, the keyword we define to tell the interpreter we have a function. Then we need a name of the function. And like variables, that's one we'll make up. So that one is going to follow, in this course, the weekly naming conventions. We're in Module 3. We'll get to the example. We'll talk about that when we get to the examples here in a moment. But that's something we make up a name for, a name so we can ask for that function. The third thing in the method header is any parameters inside of parentheses. Any parameters we'll need for this method to run. What does it need to have passed into it in order to run? Any parameters, and we'll put those inside parentheses. And the last thing in the method header is going to be a colon. Just like we saw with the if and while, and we haven't really looked at for in the example. The book covered it. We'll get into for loops later this week. The second part of the third module here is lists and getting started in those. And for loops are a lot more useful there. So we'll see that soon. But the keyword define, the name we're going to refer to it by, any parameters we'll need, and then a colon. And I'm going to go ahead and erase this generalized recap here. Just when to use functions. Obviously, it's one of our invocation structure to be reusable and organize things. So our method body is a little bit easier. It's code like we've been writing. We've seen several cases of how to feed instructions in Python. We just put up the instructions, and just like we saw with the while and if blocks, define the block by indentation. Which means when we're done with the function, we just undo the indenting. That's how we mark the end of it. And again, everything in Python is going to be passed by value. And it's going to look like what we've been doing, just inside the, we'll just indent those instructions when we want to put it inside a method. And then when we're done with that method, undo the indenting. So one other little thing of note here is global variables. So if we have global variables in our program, we can access them. We can see what they are from inside a method, but we can't change them. Can access, but not change. Unless we put the keyword global beside it, inside the method. So maybe up at the top, we'll have x equals 4, a whole bunch of other code, and somewhere we're going to have a method define m. Not going to pass anything in. And in here we want to use x. So we'll say y equals x plus 3, which we can do. We can access it. But if we want to change x, if we want to come around and turn x into something else, we have to add a keyword in. We have to explicitly state we want the global x. So that explicitly states we're referring to this, and then we can do that same thing, y equals x plus 3, and then we could change whatever x is. Just a quick example here. We're going to get into examples before long, but if we want to change a global variable, we have to make sure and put this keyword in there. I guess I don't need to erase that. So we can access but not change unless we use the keyword. We use keyword global. And personally, my own personal style, I just always go ahead and use global. I always put that keyword in there even if I'm not going to change it, because obviously that's going to show up in debugging. So it offers a layer of protection to keep us from changing that, but so does thoroughly debugging your program. I feel like offers the same level of protection. So my style, I just always put that in there. That way I don't have to worry about it. And, not just on the first pass initial design. If something comes back and changes, I don't have to worry about it. If there's a global variable, I already set it up that way, basically. That's just my personal style, something I've found to be helpful more often than it's not. Well, I guess the last little point here, I don't really need to write on the board. I ran out of room. Can I stand somewhere and still see most of the stuff? Yeah, that example's kind of there. The final note had to do with, before we get to examples, was talking about putting the modules in another file, .py file. We'll see this more explicitly when we get to the examples. But the computer has to be able to find it, because then we can just import that other file we write. And there's two ways we can do that. We can either put it in the same directory, or we could go ahead and install it with the rest of our Python library. It's going to be a couple weeks still before we see installing more stuff in the Python library. So if you want to put your methods into a separate module and import them, just make sure you put it in the same directory. So kind of getting into project stuff here, where you'll want to put things together in a folder package that way everything's together packaged the way it needs to be. So just remember that if you're going to put your methods in a separate file, that way you don't have to worry about what order they go in. For now, just put it in the same directory. Make sure it's in the same directory, which kind of makes sense anyway, right? If it goes with that project, it should be in the folder with the actual program. But that's kind of the main points. So I guess we're ready to get into some examples and see this in practice. The main point is that global thing, however you want to do it. It's there as a layer of protection so we don't accidentally change that. Personally, I like to always include it. And otherwise, we just need our keywords in the header and then indent the instructions like we've been doing. So this has probably gotten kind of long, so I'm going to go ahead and see how long this is and probably do a part B for the examples. And we'll get in over methods. And then I'll get these posted as soon as I can.